Okay, so this example is about how to do a curve sketch. Basically, a curve sketch is just a way of taking everything that we've done and putting it together to get information about the original function. So we see this original function right here, but we think we don't really know what that graph looks like. So the question is, what can we do to figure out what this graph looks like? So we start with just looking at the normal graph and figuring out what we know about the normal graph. So I'm going to start by just listing out what you're going to do for each of these things. For the x-intercept, that's going to be when the y is set equal to 0. So that's going to be something comma 0. And the y-intercept is going to be when the x is set equal to 0. So that's going to be 0 comma something. So why don't we start here with the y-intercept right here, y set equal to 0. And if we set the y equal to 0, which is this, right, we're really just setting the top of the fraction to 0. So 2x plus 2 equals 0, or rather. Yep. So that's going to be, we need to find the x that makes the y, the whole function, 0. And the whole fraction 0 when the top is 0. Think about that. The whole fraction 0 when the top is 0. So we know that x is going to equal negative 1 here. So our x-intercept is negative 1 comma 0. Let's go to the y-intercept. So for the y-intercept, we have to set our x equal to 0. So if we set our x equal to 0, we actually get 0 plus 2 over 0. We get 2 over 0, which is undefined. So I don't think there is a y-intercept. It's not defined. It does not exist, DNE, so I would say not applicable. So again, x-intercept, set the y equal to 0, which is the top of the fraction usually. Set the whole function to 0, which is usually the top of the function. Or y-intercept, just set the x equal to 0, or the x's to 0, and find the y. In this case, not applicable. So that's what we do with the original function. It shouldn't be anything new or crazy. Now we're talking about asymptotes and discontinuities. So there are a lot of those. I guess what you want to look at is, look at the denominator equal to 0 inside of a square root, or of an ln, or of a trig, right? These are the kind of things we want to consider. Well, we don't have to look at much except for the denominator. And we know when the denominator is equal to 0, we'll have a vertical asymptote. So we have a vertical asymptote, VA, when x is equal to 0. Because the bottom equals 0 when x equals 0. No square root to worry about, no ln, no trig. So really our only discontinuity is that asymptote. And we can kind of leave it at that. Okay, so feel free to pause the video as I'm writing things if you need to write all the rules. But that's basically what I'm going to do. I'm going to erase because I don't have a lot of space. Now we need our critical numbers. Well, now we have finished up with the original function, and we are now moving to the derivative. So let's just put a line here so we can kind of see what's going on. We've now done everything that we know about the original function, really, and we're going to move on to the derivative. Okay, and here we're going to be dealing with the derivative until there. Okay. So let's deal with the derivative now. So let's just take the derivative, f prime of x. Quotient rule, so derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. Well, I see here that it's going to be negative 2 over x squared for y prime, or f prime of x. So what is my critical number? Well, I simply have a critical number when the top is equal to 0, which never happens, or when the bottom is equal to 0, which is x equal to 0. That's a critical number, which makes sense because it's an asymptote. All the asymptotes are going to have something weird happening at them, right? Something's going to change or shift. There's going to be something different. So whenever you have a discontinuity or an asymptote, guess what? It's going to be a critical number, and it's going to be a not an inflection point, but a possible inflection point. So if you want to put possible point of inflection down here, x equals 0 would be another possible point of inflection. Immediately, whatever number comes out here for a vertical asymptote is going to show up as a critical number and a possible point of inflection. Okay. We have our critical number. That's the only critical number we have, so I guess right now we need to figure out increasing, decreasing, so we're going to need to make a number line, of course. A number line labeled y prime with a 0 on it. -1 and +1 seem to be good candidates. I'm going to plug them into my derivative, which is here in the circle. Okay. Well, I plug in -1, I get a negative. -2 over +1. And when I plug in +1, I get -2 over +1, so I have a negative here. So I want to say it's not increasing, but it's decreasing from -infinity to 0, and from 0 to infinity. Which means there's no relative max, because y prime doesn't change signs, right? It would have to be positive to negative or negative to positive to be a local max or a local min. So I don't see a local max or a local min happening here. That's not applicable, that's not applicable. Okay, so we've done all the work we need to do with our first derivative. So I'm going to clean this up a little bit, give us a little space to work on our second derivative, and see what information that can give us. So every derivative and original function is going to give us some information about the original graph, right? It's all going to be helpful in the end. So now we're on to the second derivative, okay? I didn't do a great job in the color coding here, but if you think about it, actually, all of this stuff right here is pertaining to the original function, right? All of this stuff here is pertaining to the derivative, and now everything here is going to be pertaining to the second derivative, really, right? Second derivative. Okay, so cool. So now let's find our second derivative. So we kind of coded things, color-coded things, rather. We'll even code that as second derivative, possible point of inflection, right? Oops, didn't work. Not the greatest use of my time during this video, but it is what it is. Okay, so we got that going. So, all right, so now let's look at our second derivative. Y double prime. Derivative of the top is 0 times the bottom minus derivative of the bottom times the top all over the bottom squared. So I have 4x over x to the 4th for my y double prime. And now we're going to need to analyze that. So again, the only thing that we have on that number line, the y double prime, we have x equals 0 is the only time. Even if in the top and in the bottom, that's the only possible point of inflection. And we need to plug in -1, and we need to plug in +1. We plug in -1, we get a negative divided by a positive. We plug in positive when we get a positive divided by a positive. It looks like that means we have, this can't be a point of inflection at x equals 0, because it's an asymptote. There's no point there at x equals 0. We talked about that earlier. But we can figure out our concavity. It's concave up from 0 to infinity, and concave down from -infinity to 0. And that's really it. Then we'll sketch the graph. We'll talk about that later, but just do your best for now. Draw in your asymptotes, draw in the points you have, make it increase and decrease. Concavity is a little harder to draw, and we'll talk about that more later in class. But for now, I just want you to get some practice in. See you soon.